Let me welcome you to this lecture. We have now seen the kind of mathematical groups that are formed by different combination of symmetry operations, as well as we have looked at the systematic procedure to determine the point group of different molecules, how one has to evaluate the presence of different symmetry operations and then decide the point group of a particular molecule. So during this lecture, we will try to find out the point group of a few molecules, and of course this finding point groups becomes more and more easy as you practice more number of molecules, or you try to deduce the point group of as many point group molecules, and it will help you. And this particular lecture is only for demonstration purpose, and it will allow you to or maybe we can look at how one can possibly look or identify or try to find the different symmetry operations in different molecules and then decide the point group of the molecule. So let us begin this lecture with a very simple molecule, that is hydrogen peroxide. So if you look at hydrogen peroxide, it can the equilibrium configuration of hydrogen peroxide is there is a OO bond, and one of the hydrogen atom, if I place both the oxygen atoms on the plane of the board here, then one of the hydrogen atom will lie above the plane of the board, while the other hydrogen atom that is attached to the other oxygen atom will lie below the plane of the board. So this is the hydrogen peroxide molecule, and one can also try to draw the molecule by looking at the molecule through the oxygen-oxygen bond, or if you place your eye over somewhere over here and then look at the hydrogen peroxide molecule, then it will look somewhat like the water molecule only. If I look at the hydrogen peroxide molecule through the oxygen atom by placing my eye somewhere over here, so we will see one of the oxygen atom, say this oxygen atom, and we will see the hydrogen atom it over here, or you can place it because it will be on the plane of the board itself, and the other oxygen atom will lie exactly below this oxygen atom, and it will not be visible. This oxygen atom will not be visible to us if we look from the hydrogen peroxide molecule from this direction, but we will just write the edge of this oxygen atom, and then this hydrogen atom is attached to this oxygen atom, the oxygen atom that is below in this particular fashion. So that is what will be visible to us, and now we can recognize that the hydrogen peroxide molecule looks more or less like the water molecule only, and there is only one C2 axis of symmetry which bisects the OO bond and passes through the hydrogen peroxide molecule in this way. So it passes through the it bisects the OO bond and passes through the hydrogen peroxide molecule in this fashion. So if we now do a C2 rotation with respect to this particular axis, we will get indistinguishable configuration in this case. Apart from this C2 axis of symmetry, no other element of symmetry is present in this hydrogen peroxide molecule, and that is why it belongs to the CN point group, and the point group for hydrogen peroxide is going to be the C2 point group. As we have already learned that for CN point group, the number of symmetry operation is equal to 2n, n only, that is the so in this case there are going to be two cells. The symmetry operation, the one is going to be the C2 operation, and the other symmetry operation is going to be the identity operation, that is C22. So only two symmetry operations are present in this point group, and the point group of hydrogen peroxide molecule in equilibrium configuration, that is this configuration, is C2. So let us now try to find point group of a slightly more complicated structure, that is, if we take the Trizero Chromate ion and try to find out the point group of the Tris-oxidative chromate ion. So what the chromium, let us draw the structure of this compound. Let us draw the octahedron first. So donor atoms are oxygen, and then we have the, let's draw the oxalato ligands. So this is the structure of Tris-oxidative chromate ion. Now if you try to find out symmetry operations in this particular molecule, what you will find, or if you look for presence of any proper axis of symmetry in this compound, what you will find is that there is a C3 axis of symmetry, and to identify the C3 axis of symmetry, one needs to find out the, as we have learned already, that in case of octahedron there are 4 C3 axis of symmetry which passes through the center of the opposite triangular faces, but as this is the symmetry has been now lowered than pure OH point group, and in this case there is only one C3 axis of symmetry, and if you consider this triangular face of the octahedron, then the opposite triangular face will be constituted by these oxygen atoms, as you can see over here. And now you can pass a C3 axis of symmetry, or what we can do is that we can also draw the structure in a slightly different way that will also allow us to deduce the C3 axis of symmetry in more clear view. That is, if we take let us not draw the oxalate ligand completely, and instead draw it in this fashion, because this atom is on the plane of the board while this particular oxygen atom is behind the plane of the board, so it is being drawn. So bold bonds towards this oxygen atom while thin bonds towards this oxygen atom which is behind the plane of the board. Same we are going to do in this case as well. And now you can see the triangular faces more clearly, but you can as well do number these atoms, maybe 1, 2, 3, 4, 5 and 6, and let us draw the triangles now. Triangular faces, that is, first triangular face or the top triangular face is formed by O1, O3 and O4. So let's put it as 1, 3 and 4, while the triangular face that is below is formed by O2, O5 and O6, and that is present in this fashion. So that is 2, 5 and 6. You can also connect them in this fashion now. So now it is obvious that there is a C3 axis of symmetry which passes through the center of these two triangular faces, that is formed by the elements, the donor atoms at position 1, 3, 4 as well as position 2, 5 and 6. So this is a C3 axis of symmetry, we know. Now it passes through the chromium atom, and as you can see, when you do rotation, so one will move to the, when you do a C3 rotation, one will move to the position of 3 while 2 will move to the position of 6. Similarly, 3 will go to 4 and 6 will go to 5, and 4 and 5 will come to the place of 1 and 2, and that is how we can we are going to get a indistinguishable configuration, you should do these exercise. You should do this rotation and then verify whether we reach an indistinguishable configuration or not when we do a C3 1 operation or say C3 2 operation in this case. So in any case, you are going to find that we do get to the indistinguishable configuration when we do C3 operations or operations generated by the C3 axis of symmetry. So now we should look for the condition that whether there are three C2 axes of symmetry are which are perpendicular to the proper axis of symmetry of highest order is present or not, to decide whether it belongs to D point group or C point group. And if you look carefully now again, what you will find that there are three C2 axes which are perpendicular to the C3 axis of symmetry, and they passes through the chromium center once again, and they lie between the triangular faces actually. It passes, the first C2 axis passes through in this direction. So this is how the first C2 axis passes through. It goes through, goes below 3 actually and above 5 and through the chromium atom. And then there is another C2 axis and there is another C2 axis in this direction. The C2 axis of symmetry are sandwiched between the two triangular faces that we must remember. They do not pass through the donor atoms and are perpendicular to the proper axis of symmetry, that is the C3 axis of symmetry. So we do have three C2 axes which are perpendicular to the C3 axis of symmetry. Now we should now look for whether there are any plane of symmetry in this molecule to decide which category of D point group it will be. So if you look carefully, you will find that there are no plane of symmetry in this particular molecule apart from the C3 axis of symmetry and the three C2 axis of symmetry which are perpendicular to the C3 axis of symmetry. There are no other plane of symmetry in this molecule, and therefore the point group of this molecule is D3 point group. So as such, we know that for a D3 point group or for a Dn point group, the total number of symmetry operation is equal to 2n because Cn will give us n symmetry operations. So C3 gives us C31, C2, and C3, which is identity, and there are three C2 axes of symmetry. So we get 3 C2. So the total number of symmetry operations is equal to 6, as we have predicted. That is 2 into 3 is equal to 6. Symmetry operations should be there in a D3 point group, and we have found all the 6 symmetry operations in this particular molecule, and it belongs to the D3 point group. So what you have seen is that one needs to visualize the molecule or try to simplify the molecule to look for symmetry operations within the molecule. Let us now take another example, which is again obtained from the octahedron by reducing the symmetry. That is, if we take facial OS CO3 Cl3 molecule. So facial isomer it is. So we will take OS. So one type of ligand will occupy one triangular face, that is why it is called facial. So let us put the carbonyl ligands in one of the triangular faces, or you can also choose to do it the way we did it last time, that is to put the ligands on the face which is pointed towards us, and the other type of ligand is Cl in a triangular face which is behind us. So that is a facial molecule. Now once again what we have seen, we see that we can draw the same structure, the triangular faces. that is this triangular face, and the other triangular face containing the Cl atoms is this one. So we can put these COs over here and these Cls over here. So once again, you can easily identify that there is a C3 axis of symmetry in this molecule, which passes through the center of these two triangular faces, and of course it goes through the osmium atom in this case. And also, apart from the, so there is a C3 axis of symmetry. So let us now also try to find if there is a there are C2 axis perpendicular to the C3 axis of symmetry or not. If you try to do so, like we did it for the last molecule, here in this case, if you do a C2 rotation with respect to a C2 axis which is sandwiched between the two triangular faces, passes through the oxygen atom, that is why, and goes via in this direction, you will find that the bottom triangle will come to the top while the top triangle will go to the bottom, and that is why we will not get, if we do that C2 operation with respect to this, what we will get, the CO will come over here. So the top triangle will go to the bottom, and yes, what it is going to look like is this. So this is going to be this CO 1, 2, 3 if we level this way, and 4, 5, and 6 if we level say. Then 2 CO, or let us level the way we did it in the last example so that there is no confusion. 1, position 1, 2, 3, 4, 5, and 6. So 3 will reach here. So this is 3, and this is going to be position 1, that is CO again, CO ligand, while this is going to be the position of CO4. So this triangle, top triangle will go to the bottom because we have done 180-degree rotation with respect to the C2 axis over here, and the bottom triangle will come up while this Cl, this is going to reach over here. So this is Cl and this is position 5, while this is going to be Cl position 6, and this is going to be Cl position 2. So now what we have seen is that we can distinguish these configurations from the initial configuration when we did the C2 operation, and it is why this C2 axis of symmetry do not exist. So since there is and there are no C2 axis of symmetry which are perpendicular to this C3 axis of symmetry is present in this molecule. So we can rule out D point group in this case, that is why. And now we should look if there are any plane of symmetry in this molecule. We can again rule out the presence of sigma H, which is our plane of symmetry perpendicular to the C3 axis of symmetry, because the top triangle will come to the go to the bottom, while bottom triangle will come to the top if we do sigma H, and that is not a symmetry operation. But there are vertical planes of symmetry which contain the C3 axis of symmetry. So if you have a plane of symmetry which bisects the molecule in this way, so that is going to give us, this will go over here, this position will come over here. Similarly, the Cl at 6 position will go to the position 5, while Cl2 and CO at 4 position are going to remain where they are. So that will give us essentially indistinguishable configuration, and this sigma V is a symmetry operations. Now since we have found one sigma V, then there must be total n sigma V, so 3 sigma V's in this molecule. So through this particular point, again there is another sigma V. If you bisect the molecule over, through a plane passing through the Cl and the osmium atom over here and the CO over here. Similarly, you can also bisect the molecule with a plane which passes through the CO at position 1, the osmium at the center, and the Cl at 6th position, and that will also be a symmetry operation. So total there are 3 sigma V plane of symmetry in this molecule, and that is why the point group is going to be C3V in this case. So we have C3V molecule for OSCO3 or facial OSCO3 Cl3 molecule. And also if you count the number of symmetry operations in this case should be equal to 2n once again, because for CNV point group we have learned earlier the number of symmetry operation is equal to 2n. So 3 symmetry operation from C3 axis of symmetry, C31, C32 and identity, while 3 and if you add the 3 sigma V, you will have total 6 symmetry operations, which is equal to 2 into 3 again. You get the 6 symmetry operations of the C3V point group. Let us now look at another complex, that is tetraazido copper, the structure of which is going to be square planar, and the azido ligand is like this. So this is what is tetraazido copper, and again in this case one can find out that there is a C4 axis of symmetry very easily. That there is a C4 axis of symmetry, and total 4 operations are going to be generated by this C4. This C41, C42, C43, and C44 is going to be identity. Again, C42 is equal to C2, so there is a collinear C2 axis of symmetry as well. So 4 symmetry operations from here. Then apart from C4 axis of symmetry, again if you look for C2 axis perpendicular to the C4 axis of symmetry, you will find that there are none C2 axis perpendicular to the C4, and so we can again rule out D point group in this case, and the point group is going to be C point group. Now we should look for a plane of symmetry in this case again, and if you look for plane of symmetry, what you will find that there are no sigma V type of plane of symmetry, but there is a sigma H plane of symmetry because the molecule is essentially planar, and this plane containing all atoms of this molecule, which we can also call as the molecular plane of symmetry, is essentially perpendicular to the C4 axis of symmetry, and that is why it is a sigma H plane of symmetry. So it is sigma H plane of symmetry is there in this case. Apart from that, we have no other symmetry element is present in this molecule again, and therefore the point group in this case is going to be not B4H but C4H point group. But again, what we should look carefully is that the combination of C4 and the symmetry operations generated by C4 and sigma H are essentially symmetry operations generated by an S4 axis of symmetry. So along with a C4 axis of symmetry, collinear to it is an S4 axis of symmetry is present, and that is the symmetry operations generated by the combination of C41 sigma, C42 sigma, C43 sigma, and C44 sigma. They are all must be present here. So this is equal to sigma only, that is sigma H that we have already considered, while C43 sigma is going to be S43 of symmetry operation. C42 sigma is going to be S2 symmetry operation actually, and which is equal to inversion center, and this is S4 1. So all these symmetry operations are also present along with the symmetry operations of C4 and the sigma H. So if you count all these symmetry operations, what you will find that there are total 4 symmetry operations from C4, sigma H, that is 5, and then 6, 7, 8. Total 8 symmetry operations are present in these molecules. This sigma H we have already counted, so that is why we are not counting this once again. And again, the way we have predicted that CNH point groups will have 2n symmetry operations, we have found that this particular molecule, which belongs to C4H point group, it has total 8 symmetry operations, that is, and we have also listed all the symmetry operations. Let us now choose a molecule whose name is very interesting. Its name is Coronin, and if you look at the structure of this molecule, that is even more interesting. There are 7 fused benzene rings in this molecule. And you can also write the hydrogen atoms so that there is no confusion about the structure of this compound. And now let us try to deduce the point group of this molecule. So one can easily find out the proper axis of symmetry of highest order that is present in this molecule, which is the C6 axis of symmetry, and passes through the central center of the central benzene ring over here. So if again this molecule is planar, and we assume that all the atoms of this Coronin molecule lies on this plane of this board, and the C6 axis of symmetry is essentially perpendicular to the plane of the board and goes through the molecule in this fashion. So apart from the C6 axis of symmetry, let us now try to find out if there are 6 C2 axis of symmetry perpendicular to this C6 axis of symmetry to determine whether it belongs to D type or C type point group. And if you do so, what you will find that indeed there are total 6 C2 axis of symmetry perpendicular to the C6 axis of symmetry. So you can draw the C2 axis of symmetry. This is one C2. This is another C2. Then we have this is another C2, 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 and then we also have C2 in this way, and then we have C2 in this way, and then we also have C2 in this way. So these are all the C2s that we have labeled. So total there are 6 C2s that we have seen. This is one, this is the second one, third, fourth, fifth, and 6 C2 axis of symmetry are present in this molecule. So it belongs to the D type of point group because we have C6 axis, and perpendicular to the C6 there are 6 C2 axis of symmetry. So let us now try to find out if there are any sigma H plane of symmetry present in this molecule or not. Then if you do, because this molecule is planar, so the plane containing all the atoms in this molecule is the molecular plane, and that is going to be perpendicular to the C6 axis of symmetry, and that is why it is to be denoted as sigma H. So we have found C6, we have found 6C2 perpendicular to the C6, and we have also found the sigma H. So this essentially tells us the point group of this molecule is the 6H. So let us also try to find out the other symmetry operations that must be present if we have a D6H point group that we have learned. Whenever we have a Cn axis of symmetry and Nc2 axis of symmetry perpendicular to the Cn, and then if we add a sigma H, we will also have the mathematical requirement that there are n sigma v's which contain the C2 axis of symmetry, or there are going to be n sigma v is all as well, which are going to contain the C2 axis of symmetry, vertical planes of symmetry, which contain both the C2 axis of symmetry as well as the principal axis of symmetry. So this is a mathematical requirement, and we do have these 6 sigma v's, and which are along the direction of the C2 axis of symmetry. So you can bisect the molecule along the directions where we have drawn the C2 axis of symmetry, and they are all going to be, these planes are going to be vertical planes of symmetry. So we do have 6 sigma v's. Apart from that, we also have to consider the combination of these two symmetry operations, that is C6 and sigma H, which essentially gives us an improper axis of symmetry, that is the S6 axis of symmetry, and all the symmetry operations generated by the S6 axis of symmetry are also going to be present along with the symmetry operations generated by these symmetry elements. So let us quickly review the symmetry operations generated by S6 axis of symmetry. So this is going to be S61, and this one is going to be C62 sigma 2. C62 is going to be C31. This is going to be equal to C63 sigma 3. C63 is going to be equal to C2. So and sigma 3 is going to be equal to the sigma. So that is going to be equal to S2, and which is going to be equal to inversion center. You can find out that there is an inversion center in this molecule. At the center of this molecule, there is an inversion center, and we do get that symmetry operation from this axis of S6 axis of symmetry itself. So then S46 is going to be C64 sigma 4. Sigma 4 is going to be identity, while C64 is going to be equal to C32. Then this is S65 is going to remain as S65, and S66 is going to be equal to identity. So there are total n minus 1 symmetry operation, total 5 symmetry operations that are generated by this S6 axis of symmetry, and we have seen that all of these 5 symmetry operations are there is a C3 axis of symmetry collinear to the S6 axis of symmetry, and that is we can find out by deducing it from the S6 by simplifying the symmetry operations generated by the S6 axis of symmetry. So total again what we have is we have n symmetry operations from C6. So total 6 symmetry operations from C6 axis of symmetry, and then we will have also 6C2. So that is 6C2 axis of symmetry. Sigma H is one of the symmetry operation, 6 sigma V produce 6 symmetry operation, and the S6 axis of symmetry gives us 5 symmetry operations. So total what we have is 24 symmetry operations of within this D6H point group. And we have found all the symmetry operations in this molecule. So the last molecule for which we will deduce the point group is the allene point molecule, which is essentially the hydrogen atoms are on perpendicular planes, and what we have to do to find out the point group of this molecule, we have to place it inside a box again, this way. and one needs to put the hydrogen atoms in the alternate corners of this box. So the C bond is in the middle of the box, while the hydrogen atoms we can place in the alternate corners of this box. So this is H1, say H2, H3, and H4. Let's also connect these atoms. So that is how the alene molecule, to deduce the symmetry operations in alene molecule, we need to put it inside, visualize the molecule inside a cube by placing the hydrogen atoms in the alternate corners of the cube. And if you do so, what you will find that you can easily deduce that there is a C2 axis of symmetry along the CCC bond in this molecule. It passes through the, so it goes this way. So this is the C2 axis of symmetry, as well as collinear to this C2 axis of symmetry, there is a S4 axis of symmetry. So one may think that the point group in this case is S4 point group, because the C2 has evolved or is there because the S4 is an even number, even order improper axis of symmetry, and as a result of S4 only C2 axis is present. But apart from the S4 axis of symmetry, there are other symmetry operations present in this molecule, and that is why the point group is not going to be S4 but something else. So what we can find, like the way we have done in case of tetrahedron, in this case as well, there are three C2 axis of symmetry. One C2 axis of symmetry goes to the center of this face and goes away from the center of the opposite face over here, while if we take the top face over here and the bottom face of the cube, then again and an axis which passes through the center of this top face and goes out through the center of the bottom face and goes through the this middle carbon atom is again going to be a C2 axis of symmetry, because when you do 180-degree rotation with respect to this axis, H1 will reach H4, H2 will reach H3, and vice versa, and that is why that is going to be a symmetry operation. And similarly, if you also consider an C2 axis of symmetry which goes through the center of the top face over here and the center of the bottom face, then again that is also going to be a C2 axis of symmetry, because again when you do C2 rotation, 180-degree rotation with respect to this axis, H1 will reach H3 and H4 will reach H2, which is going to be when we will get to the indistinguishable configuration. So total there are three C2 axes of symmetry, and these C2 axes of symmetry are perpendicular to each other. So if we consider this particular C2 axis, which goes through the which is molecular axis or goes through the carbon-carbon-carbon bond to be the principal axis, then these two symmetry axes are C2 axes are perpendicular to the C2 axis. So we consider this C2 axis as the principal axis, and there are two C2 perpendicular to the principal C2 axis. So again we will have a D point group in this case. Now we should look for if there are any plane of symmetry in this molecule. Now if you consider a plane which bisects the molecule and perpendicular to the this principal axis, C2 axis, over here you will realize that this, and if we do reflection, this hydrogen will reach over here. So, and there is no hydrogen over here, and that is why that is not going to be a symmetry operation. So there is no sigma H in this molecule. So we should now look for, since sigma H is absent, so sigma V is also going to be vertically, is also going to be absent mathematically, and we should look if there are diagonal planes of symmetry or plane of symmetry which bisect the angle between two C2 axes of symmetry or not in this molecule. So now if you assume a C2 axis of symmetry which contain these two hydrogen atom or bisects the cube in this way, slice the cube in this way that it contains these two hydrogen atoms, then upon doing reflection with respect to that particular plane, the CCC, these three atoms are also going to be present inside the plane, and that is why they are not going to move. These two atoms, since they are within the plane of the symmetry, they are also not going to move when we do reflection. But H4 will come to H3 and H3 will come to the position of H4 when we do reflection with respect to that particular plane of symmetry, because it will bisect the cube in this fashion, because here, and this portion will come over here, this one will go over here, and that is a sigma d plane of symmetry, because this plane, again, if you look carefully, what you will find, it bisect the angle between these two C2 axes of symmetry. So it's a diagonal plane of symmetry, and similarly along these two, or containing these two hydrogen atom and these three carbon atom as well, there is a diagonal plane of symmetry which again will bisect the molecule here over here, and the reflections will essentially replace the hydrogen atom. H1 will come over here, H2 will come over here. So there are total 2 sigma d plane of symmetry in this molecule, and these sigma d's do bisect the angle between the two C2 axes of symmetry, as we have said. The sigma d's in these cases must bisect the angle between the C2 axis of symmetry, which are perpendicular to the proper axis of symmetry of highest order. So the point group in this case is again D to D point group, and as predicted earlier, it does have a S2M axis of symmetry, that is the S4 axis of symmetry in this case, and there are going to be total n symmetry operations are generated by the S4 axis of symmetry, that is S41 and S43. These are the distinct symmetry operations generated by the S4 axis of symmetry, and that is why what we have total, again in this case as well, we have total 4n symmetry operations, and this number of symmetry operations is going to be equal to 8 symmetry operations, as we have already found out in this case as well. C2 operation, this is total 3 C2 operation, so 2 sigma d operation, so that is equal to 5 symmetry operations, and then we have the S41, S43, and as well as we have the identity, and that makes the number equal to 8 symmetry operations. So the symmetry point group in this case is D to D, as we have found, C2, 2 C2 perpendicular to C2, and there are 2 sigma D plane of symmetry in this molecule. So what we have seen, again, how one can find out the point group of alene molecule by considering the atoms to be, the hydrogen atoms to be at opposite corners of a cube. So this brings us to the end of this lecture. What we have essentially seen during this lecture is how one can find out point group of a few molecules, and what we have seen, we can use the systematic procedure to determine point group of molecules, and thereby find out the point group of different molecules. And we need to visualize the molecules from different angles, as well as place them in different certain geometric objects to make it easy for us to visualize the molecules. So with this, let me conclude this lecture. Thank you very much for being with me during this lecture.